Welcome to a project of cryptography. The topic of our project is implementation of threshold signatures using different schemes. These are the table of our contents. So let me just give you an overview and introduction to your project. Let's consider a group of n users P1, P2 up to Pn. A threshold signature scheme TSS enables any subgroup of T plus 1 users to jointly generate a signature, but any subgroup with size T or less cannot. A TSS consists of three algorithms: threshold key generation, threshold signature generation, and verification. Here we have used the ECDSA scheme, which stands for elliptic curve digital signature algorithm. ECC, which is elliptic curve cryptography, is a public key cryptographic technique that uses the mathematics of elliptic curves to provide encryption and digital signatures. The elliptic curve is a set of points that satisfy a specific mathematical equation. The cryptographic strength of ECC comes from the difficulty of solving the underlying mathematical problem known as the elliptic curve discrete logarithmic problem (ECDLP). In ECC, each user has a public and a private key. The public key is a point on the elliptic curve, and the private key is a secret number that only the user knows. To encrypt a message, the sender uses the receiver's public key to compute a shared secret. To decrypt the message, the receiver uses their private key to compute the same shared secret. Here, as we can see that Bob is sending a message to Alice, and we have used a hash function, a key pair which consists of private key sk and public key pk, and k, which is a constant, which are random nonce, to generate a signature, which is then verified using this equation which is given the screen, and then the message sent to the Alice. Here we can also see that G is a point on the elliptic curve, and QA, which is a public key, is DA.G, where DA is a private key, and DA is a constant integer. The ECDSA algorithm that we have used is described on the screen. Say Alice signs the message with the following. First, create a hash of the message E equal to hash M. Second step is let H be the ln with the leftmost bit of E. ln has a bit length of group order n. Third, create a random number k which is between 1 and n minus 1. Fourth is calculate a point on the curve as x1, y1 equal to k cross g. Fifth, calculate r equal to x1 mod n. If r equal to 0, go back to step 3. Then the next step is calculate s equal to k minus 1 h plus r dA mod n. Here if s equal to 0, then we have to go back to step 3. Seventh, the signature is to pair r comma s. Here we can see that signature is generated. Now the Bob will check using the following steps. First, create a hash of the message E equal to hash M. Second, let H be the ln leftmost bit of E. Third, calculate C equal to S minus S inverse mod n. Fourth, calculate U1 equal to H dot C mod n and U2 equals to R dot C mod n. Fifth, calculate the curve point x1 y1 equal to u1 cross g plus u2 cross qa. If x1 comma y1 is equal to 0, then the signature is invalid. The last step is the signature is valid if r equivalent to x1 mod n, invalid otherwise. We can see that equation given below. Moving on to a threshold signature using ECDSA scheme. The algorithm is performed in three parts, which includes key generation, signing, and verification. Key generation. First, we have to select an elliptic curve E and a generator point G on that curve. Choose a large prime number Q as the order of the generator point G. Choose a random number K for each of n participants, where n is the total number of participants. Each participant calculates their own public key Pi as Pi equal to Ki cross G and keeps their secret key Ki. The group public key is a sum of all public key P equals to Pi P1 plus P2 and up to Pn. Signing. The group chooses a threshold value T and selects any T out of n participants to be signers. Each signer generates a nonce value Ri and computes Ri equals to Rig. Each signer computes their own partial signature Si. The group combines the partial signatures using a Lagrange interpolation polynomial to get the group signature S, which is given by the equation. Group signature is R, S. Verification. First, we have to verify that R is a valid point on the curve. Second, calculate the group public key, which is given by P equal to P1 plus P2 up to Pn. Third, calculate the inverse of the group public key, P inverse. Compute the hash value of the message. Calculate the two values U1 and U2. Compute the point Q. If Q is equals to R, the signature is valid. Otherwise, the signature is invalid.
Okay, so now we'll look at the code. Implementation of ECDSA threshold scheme in Python. The first code depicts ECDSA scheme. Here, the code uses SECP256K1 elliptic curve, which is standard curve often used in cryptography. This curve is defined by following parameters: P, comma, A equals to 0, B equals to 7, N, H equals to 1, G. These parameters define an elliptic curve in the form of y square equals to x cube plus 7 over the prime field of group order P, where P is large prime number. The point gx comma gy equals to G is a fixed generator point on the curve, and N is the order of the subgroup generated by G. This curve is widely used in the practice and particularly in the Bitcoin blockchain. Now we'll look at the functions which are used in the code. So first, the elliptic curve named tuple represent the elliptic curve parameters required for the ECDSA algorithm, including the field characteristic P, coefficients A and B, base point G, suborder N, and cofactor H. Now here is the inverse mod function. What it does is the inverse mod function computes the inverse of number modulo prime number p. This function is used to perform modular arithmetic required for ECDSA algorithm. Now we'll look at this function is on curve. This function verifies if a point is on elliptic curve. The point add function add 2 points on the elliptic curve and returns the resulting point. The scalar mult value function computes the scalar multiplication of a point with an integer. This the make key pair function generates a random private public key on elliptic curve. The sign function generates a digital signature for a given message hash and random number k using the private key secret, and verifies function verifies a digital signature for a given message hash and a public key. The verifies function first checks if the signature components R and S are within the range 1 comma n minus 1. If not, the function returns false. The function then computes the inverse of S modulo n and the hash of the message. The function then computes the points u1 and u2 as scalar multiplication of the hash and the inverse of S and x and the inverse of S respectively. The function then computes the point p as the sum of u1 and u2 using the point add function. The function then returns true if the x coordinate of a point P is equals to x and false otherwise. Okay, so let's look at the next part of the code, threshold signature with ECDSA scheme. This Python code implements the ECDSA for threshold signatures. The threshold signature scheme allows multiple parties to jointly generate a single signature on a message, and the signature is valid only if a minimum number of parties participate. In this implementation, we have n signers, and the threshold is set to t. So, to implement this algorithm, firstly we need to install the necessary package ECDSA. As we can see, we can use the command pip install ECDSA to install the ECDSA package. And then we imported the necessary libraries for to work for our requirement. Now, the ECDSA class has the following methods: the init method, which takes three arguments: self, T and N, initializes the ECDSA class with the threshold value T and the number of signers N. It also initializes the signing key SK and the verifying key VK list for all N signers. Then we have another function called keygen, generates key pairs for all N signers using the signing key.generate method from the ECDSA module. Returns a list of tuples containing the signing key and verifying key for each signer. Then we have share function which takes arguments self and sk signing key. Generates secret shares for a given secret key sk using the Shamir secret sharing scheme. Returns a list of signing key objects corresponding to all the signers. Then we have sign function sign method which generates an ECDSA signature for a given secret key sk and message using the sign key.sign method from the ECDSA module and then returns the signature bytes. Then we have aggregate function which takes arguments as self and SIGs, aggregates the individual signatures of for a message by concatenating them and hashing the results using SH8256 and then returns the aggregated signature bytes. Then we have verify function which takes arguments as self, aggregate, message and PKs. The verifies the it this function verifies the aggregated signature on a given message with the public keys PKs of all signers using the verify key dot verify method from the ECDSA module and then returns a boolean value indicating whether the signature is valid or not. Now, the above code generates key pairs for all three signers, generates a secret share for signer one, generates a signature for signer one on the message "Hello World," generate signatures for the remaining signers, aggregate all signers, and verify the threshold signature using the public keys of all signers. Here we can see the output. The signature is valid. Is signature valid? False.
Let us see the threshold signature using Schnorr scheme. So as you can see in this diagram, we have Bob and Alice. Bob is sending a message M to Alice. That message M is diverted to the Schnorr signature where it takes the value R and S, where it then goes to the function check signature. In the check function, we are checking p dot hash m parallel to r plus s dot g is equal to r, which checks whether our signature is valid or not. And for that process, we have here, as you can see, the key pairs, for which we have the public key, where p is equal to sk.g, and private key sk. Also, we have a select random k value, which goes into this function where we can see here, where r is equal to k dot g and ks is equal to k minus hash function of m parallel to r dot sk. Now this, as you can see, this Schnorr signature scheme is also based on discrete logarithm. The Schnorr scheme minimizes the message dependent amount of computation required to generate a signature. Also, the main work for signature generation does not depend on the message. The scheme one is based on using a prime modulus p with having a p minus 1 prime factor of q appropriate size, that is p is equal to 1 modulo q. Typically, we use p is equal to 2 raised to the power 1024 and q is equal to 2 raised to the power 160. Here, as you can see, 1024 and 160 are the numbers of bit conventionally. And now this process includes the following step. First, we have the key generation, next we have the signing, and third we have the verification. Now let us see how we calculate the first at the sender side. First of all, we choose primes p and q such that q is a prime factor of p minus 1. Then we choose an integer gamma such that gamma raised to power q is 1 modulo p. The values gamma p q comprises a global public key that can be common to a group of users. Then we choose random integer s with S being greater than 0 but less than Q, which is the sender's private key. Next, we calculate V is equal to gamma minus S modulo P, which is the sender's public key. Then we choose a random integer R such that R is greater than 0 and less than Q, and compute X equal to gamma minus R modulo P. And this pre-processing stage is independent of the simple text M to be signed. Next, we attach the message M with X and hash the attached resultant to compute the value. Here we have E value, which is H, which is attaching the simple text M with X. H here is the hash function. E is the hashed value of the simple text M. And in the next step, we compute Y, which is equal to R plus S multiplied by E, taken whole modulo of Q. And here the signature pairs are, as you can see, is Y comma E. Next, let us see the calculation at the receiver side. Now the receiver knows that this P is the prime number, V is the public key, Q is the prime factor of P minus 1 and gamma. Now let us compute X dash, which is gamma into Y multiplied by V raised to power E modulo P. Here V is equal to modulo minus S, gamma minus S modulo P. Here, as you can see in the situation, we have the gamma into Y multiplied by gamma minus SE modulo P, and we have gamma minus bracket gamma minus SE modulo P, which means Y is equal to R plus S multiplied by E, and we get X bar is equal to gamma raised to power R modulo P. In the next step, we can see that X bar is coming equal to X. Also, we verify that E is equal to H, where M is connected to the text X. And as you can see in the last step, HMX is coming equal to the HMX dash. Now let us see threshold signature using BLS scheme. So the following is a high-level description of the mathematical derivation of the scheme. So we have three components in it. First is key generation, which is a reliable dealer creates a polynomial of degree 1 t minus 1 and a BLS key pair for each signer, where t is the bare minimum required to produce a legally binding signature. And for that, we have the Shamir's secret sharing scheme, which is used by the dealer to determine a secret share of the polynomial for each signer. Also, the associated public key is given to each signer along with their portion. Next is signing, which is to sign a message. Each signer computes a BLS signature using the message, and their secret share message is provided. A threshold signature is produced by combining the separate signatures. And the last, we have the verification of the signature, which is validated using the BLS verification method. Now let us briefly see here what key generation says. In this, we have G, which is a cyclic group of prime order P with generator G, T be the threshold and N be the total number of signers, Fx be a polynomial of degree t minus 1 over the field Zp with coefficients chosen uniformly at random from Zp, and for each signer I, compute their secret key Ski is equal to Fi and their public key Pki is equal to Gski. Next, we have the secret sharing, for which each signer I generates a degree t minus 1 polynomial Six with random coefficients in Zp such that Si0 is equal to Ski, and next we evaluate this Sij for every I and send the shares Sij along with their corresponding public key Pki to signer I. Next is the signature generation, and for which to sign a message M, each signer I computes a BLS signature using their secret share Si and the message M, where Si into Gi is equal to Hm into Si0, where H here is the cryptographic hash function, and the threshold signature is computed as the product of the individual signature. That is, SIG is equal to SIG1 times SIG2 times SIG3 till SIGT. And last, we have the signature verification, that is to verify the threshold signature SIG on the message M. The verifier checks if E SIG, G is equal to HM, PKI, PK1 into PK2 till PKT, where E is the bilinear pairing function, and if the equation holds, our signature is termed as valid. Now let us see the implementation of BLS threshold scheme in Python. Now let's look at the code. First, we import the necessary libraries hashlib for the cryptographic hash function and functools for the aggregation of signatures. Next, we define a class called BLS. The class takes four parameters P, G, T, and N. P is a prime number that defines the order of a cyclic group. G is a generator of the cyclic group. T is the threshold number of signers required to produce a valid signature, and N is the total number of signers. Inside the class, we define several methods to perform various operations. The first method is called keygen. This method generates the secret and public keys for each signer and returns a list of tuples containing SKI, PKI for each signer I. Here how it works. First, it generates a list of t-1 random integers between 0 and p-1. It appends a 0 to this list to get a total of t elements. Next, it calculates the secret key SK and public key PK for each signer. It does this by first generating an evaluation polynomial of degree t-1 with the random coefficients f0, f1 till ft-1. Then for each signer I, it evaluates the polynomial at I plus 1 to get SKI and sets PKI to be g raised to SKI modulo p. The method then returns a list of tuples where the first element is SKI and the second element is PKI for each signer I. The second method is called share. This method generates secret shares for given secret key SK and then returns a list of shares corresponding to all the signers. After generating the keys, the code picks up one signer, in this case the first one, and generates a secret share of them using the share method. This is necessary because in the threshold signer scheme, every signer must have a unique share of the secret key, and the shares are used to construct the final signature. Next, the code signs a message, in this case the string hello world, using the sign method for the selected signer. The signature is stored in the variable sig1. After that, the code generates signatures for the remaining signers using a loop that goes from 1 to bls.t-1. In each iteration, it picks the corresponding secret key from the list of keys using the index I and generates a signature for the message using the sign method. The signature is stored in the sig variable and added to the list all 6. Finally, the code aggregates all the signatures in the all 6 list using the aggregate method, and the aggregated signature is stored in the variable @sig. In the last step, the code verifies the threshold signature using the verify method. It passes the aggregated signature, the message, and the public keys of all the signers to the verify method. If the signature is valid, the method returns true and the code prints is signature valid true to the console, and the code prints is signature valid false to the console if it returns false.
So, ending our project video, let's conclude whatever we have done in the project or whatever we have learned. We have covered three different schemes used in threshold signatures: threshold Schnorr signatures, threshold signatures using ECDSA, and threshold BLS signatures. Each scheme has its own strengths and weaknesses, and the choice of scheme may depend on the specific requirements of a given application. Shamir's secret sharing is a flexible and widely used scheme that can be used with a variety of cryptographic algorithms, including Schnorr and ECDSA. Threshold Schnorr signatures offer strong security guarantees and efficient signing and verification times, making them a popular choice for many applications. Threshold signatures using ECDSA can be used with existing public key infrastructure (PKI) systems and offer compatibility with a wide range of existing applications. Finally, threshold BLS signatures offer fast signing and verification times, as well as high resistance to side channel attacks. Overall, threshold signatures provide a powerful tool for implementing distributed trust and security in a variety of settings. We encourage further exploration of the topic and hope that this presentation has served as a useful introduction to the different schemes used in threshold signatures. Here are some of the references that we have used for the project. These are the URLs that we have used or referenced for our project development. Thank you.